Hello everybody, welcome to our first online MECA 332 course. I hope you are well and healthy. This week we will first solve a question about variable loading and fatigue where we have three different cases. In the first case, we have completely reversed force F applied to the bar on the right. The yield strength and ultimate strength of the bar are 150 and 400 megapascals respectively. The endurance limit is given as 100 megapascals. Here we have the SN graph of a steel. It shows the fatigue strength S of a material with respect to the number of stress cycles N. The graph is plotted logarithmically. To establish the fatigue strength of a material, quite a number of tests are necessary because of the statistical nature of fatigue. For the rotating beam test, for example, a constant bending load is applied, and the number of revolutions, or stress reversals, of the beam required for failure is recorded. The first test is made at a stress that is somewhat under the ultimate strength of the material. The second test is made at a stress that is less than that used in the first. The process is continued and results are plotted as an SN diagram. We are going to use SN diagram to find the fatigue strength of this material, but we only know it for 10 to the power of 6 cycles, which is the endurance limit. Let's remember what the endurance limit was. It is defined as the stress level below which an infinite number of loading cycles can be applied to a material without causing fatigue failure. If we check the SN diagram again, you can see that the fatigue strength decreases linearly between cycles 10 to the power of 3 and 10 to the power of 6. We can use this linear region for estimating the fatigue strength for 10 to the power of 5 cycles. We know that the strength where n equals to 10 to the power of 6 cycles is 100 megapascals. We can approximate the strength where n is 10 to the power of 3 cycles as 0.8 times the ultimate strength, which is 320 megapascals. Knowing the values of these 2 points, we can estimate the fatigue strength of 10 to the power of 5 cycles. Remember that the graph is plotted logarithmically, so we need to use the following equation. Fatigue life equals to A times the number of cycles to the power of B. Here, A and B are constants and their values are same for both points. If we write down this equation for those 2 points, we obtain the following set of equations where we have 2 unknowns. To solve it, we take the logarithm of both sides. When we solved the 2 equations, we found A to be 1000 and B to be minus 0.167. Thus, we obtain the formula relating the number of stress cycles with fatigue strength. We plug in 10 to the power of 5 as n to our function, and we find the fatigue strength. But this is not the end of the question, as what is demanded is the safety factor. To find the safety factor, we need to divide the fatigue strength by applied stress. First, we need to convert the force load to a stress value. As the force is applied perpendicular to the tip of the cantilever beam, it creates a normal stress in the beam. To find a normal stress, we divide the applied force to the applied surface area. If we divide F to A, we find out that the normal stress equals to 50 megapascals. Then we plug in the normal stress and the fatigue strength to our safety factor formula, and we found out that the safety factor equals to 2.94. This time, we need to find safety factor for infinite life. Remember the SN curve. In the case of the steels, a knee occurs in the graph, and beyond this knee, failure will not occur, no matter how great the number of cycles. The strength corresponding to the knee is called the endurance limit, SE, or the fatigue limit. The region where the curve becomes parallel to x-axis is called the infinite life region. This time, we can find the fatigue strength easily as it is equals to the endurance limit of the material. We also know the applied stress, so again, if we plug in these values to our factor of safety formula, we found out that the safety factor equals to 2. For 1C, we need to calculate the safety factor of the design for n equals to 10 to the power 5 cycles if the magnitude of the force F varies between 0 kilonewtons and 20 kilonewtons. Here, the type of variable loading is changed. It is no longer completely reversed as the mean force or stress is not equals to 0. This means we can no longer use the SN graph to estimate the fatigue strength. The reason is most basic SN fatigue data collected in the laboratory is generated using a fully reversed stress cycle. However, actual loading applications usually involve a mean stress on which the oscillatory stress is superimposed. A very substantial amount of testing is required to generate a diagram, and it is usually impractical to develop curves for all combinations of mean and alternating stresses. Several empirical relationships that relate alternating stress to mean stress have been developed to address this difficulty. For this problem, we are going to use the modified Goodman criteria. Here we have two axes. The mean stress will be placed on the x-axis and the alternating stress magnitude will be placed on the y-axis. We will place the ultimate strength value of our material to x-axis. We place the yield strength value of our material to both x and y-axis. Lastly, we will place the fatigue strength for 10 to the power 5 cycles to the y-axis. Then, we will draw three straight lines. First, we will draw a dot at the point where the mean and alternating stresses are intersecting, which has the coordinates 50 and 50. Then, we draw a line starting from the origin, which will pass from this point. This is our loading line. Then, we will draw a straight line connecting the yield strength values on both axes. This is our yield line. The last one will start from the fatigue strength for 10 to the power 5 cycles and end at the ultimate strength value. This is our fatigue line. Using the modified Goodman criteria, we can determine the reason for the failure. The line that our loading line intersects first will be the cause of the failure. In our case, our loading line intersects with the yield line first, so that means the failure is going to be due to yielding. Using the formula for the modified Goodman criteria, we can calculate the factor of safety. We simply plug in the values that we have calculated before to the equation, and the factor of safety turns out to be 1.5. In this problem, we are given a pressure chamber that is sealed by a cover fastened with 4 preloaded bolts. The bolts are metric ton, class 5.8. The pressure inside the chamber is given as 400 kilopascals. The diameter of the vessel is 60 centimeters and the joint stiffness constant for the bolt and material interface is 0.1. We need to calculate the safety factor of bolts for yielding. That means we need to find the total load on the bolt. The total load on the bolt has two sources, one internal and one external. The internal one is caused by the clamping force that is used for tightening the bolt. That is called the preload. The external load is due to the pressure inside the chamber. We need to calculate them both to find the safety factor. Let us first start with the definition of the preload. The clamping force that had been applied to the bolt by tightening it before any external load is applied is called preload. It is denoted with F subscript I. In hint, It is said that the fasteners are preloaded up to 90% of their proof strength in static loading. And let's remember what the definition of the proof strength was. The proof load is the maximum load that a bolt can withstand without acquiring a permanent set. Permanent set means there is plastic deformation. The proof strength is the quotient of the proof load and the tensile stress area. The proof strength thus corresponds roughly to the proportional limit and corresponds to 0.0001 inch permanent set in the fastener, which is the first measurable deviation from elastic behavior. Then, it seems, we need to find the proof strength of our bolt to calculate the preload. We can find this value using table on the left. We know that the class number of our bolt is 5.8. If we check that row, we see that the proof strength is 380 megapascals and the yield strength is 420 megapascals. The proof strength is given in megapascals. We need to convert it to a force to find the preload. Remember the definition of the proof strength. It was the quotient of the proof load and the tensile stress area. So the relationship between them can be expressed with the following formula. Preload equals to K times proof strength times tensile stress area, where K is the fraction of the proof strength given in the hint, which is 0.9. SP is the proof strength and AT is the tensile stress area. We can find the tensile stress from the table on the left for our bolt. We know the major diameter of our bolt is 10 mm, as the bolt is defined as metric 10. If we check the row where the major diameter of the bolt is given as 10 mm, we can find that for a bolt with fine threads, the tensile stress area is given as 61.2 square millimeters. We can then convert square millimeter to square meter by multiplying the value by 10 to the power of minus 6. Then we plug in the values to the formula given to find that the preload is equals to 20.93 kilonewtons. The total force created in the vessel can be found with the following formula. P total is equals to P times the area of the vessel, where P is the pressure inside the chamber and it is equals to 400 kilopascals, and a vessel is the surface area. We know that the chamber has a circular surface area, so that the area of the vessel equals to P times the diameter squared of the vessel divided to 4. The diameter of the chamber is given as 60 centimeters or 0.6 meters. We calculate the area to be 0.287 square meters. Returning to our total force created formula, we calculate the total force to be 114.8 kilonewtons. As we have 4 bolts, the force applied to each bolt is equals to a quarter of the total force, which is 28.7 kilonewtons. The portion of P taken by the bolt, which is denoted with P subscript B, is equals to C times P, where C is the joint stiffness for the bolt and material interface, which can be taught as the fraction of external load carried by the bolt. It is given as 0.1. We can calculate PB as 2.87 kilonewtons. The resultant force load equals to preload plus the external load PB. We calculate the resultant force to be 23.8 kilonewtons. To calculate the safety factor, we need to find the total stress on the bolt. The total stress equals to resultant force divided by the tensile stress area. We calculate it to be 388.89 megapascals. Lastly, to calculate the safety factor, we need to divide the yield strength by the total stress applied on the bolt. When done, we calculate the safety factor to be 1.08. In this problem, we have a decompression chamber with a hemispherical window. A hemispherical window is subject to an internal air pressure P. The inner radius of the hemisphere is 80 centimeters and its thickness is 1 centimeters. The Mohr circle representation of the principal stress for a small element taken on the surface of the window is shown below. Calculate the number of bolts required to attach the window to the wall of the chamber if each bolt has a radius of 1 centimeter and the allowable tensile stress for the bolt is 150 megapascals. First, we need to check if the sphere is thin or thick-walled. When the wall thickness is less than about 1/10 of the radius, the cylinder can be considered thin-walled. The radius of our spherical vessel is 80 centimeters, which is 80 times greater than the wall thickness. That means we can consider our pressure vessel as thin-walled. In a spherical vessel, the directions for the stresses are tangential, axial, and radial. Because our vessel is thin-walled, we can make the following two assumptions. First, the radial stress is considered zero. The second assumption is the tangential stress is equal to the axial stress. We can find the values of these stresses from the Mohr circle on the left. Sigma 3 is 0, that is the radial stress. Sigma 1 and 2 have the same value and it is 20 megapascals. That is the magnitude of tangential and the axial stress as well. The pressure creating this stress can be found with the following formula. Sigma is equals to P times R divided to 2T, where P is the inner pressure, R is the radius of the sphere, and T is the thickness of the sphere wall. We know the stresses as well. Using this formula, we calculate the pressure P to be 0.5 megapascals. The total force acting on the wall of the chamber can be found with the following formula. The total force is equals to P times R squared times P. When we plug in the values, we find the force to be 1000 kilonewtons. The force will be carried by n number of bolts. We can relate the individual stress with the allowable total stress. The formula for n equals to F total divided to allowable stress times surface area of a bolt. When we do the calculation, we found n to be 21.22. But n needs to be an integer, as we cannot use a fraction of a bolt. So we round up this number to 22, which is our solution.